Okay, so in this example, let's find the rate law for this reaction, including the rate constant and the orders. Here we have two reactants rather than just one. So the rate law is the rate is equal to some rate constant times the concentration of the reactants. Here's NO raised to the N times the concentration of hydrogen raised to the M. So notice here we've got two reactants. Now we need to go find the rate constant and we need to go find the orders of reaction. In order to do that, we need to have some data. So here we've got a table with different experiments. We'll go ahead and call these experiment 1, 2, and 3. In the first column, we have the concentration of NO at the beginning of a reaction. In the middle, we have the concentration of hydrogen at the beginning of the reaction. And then here we have the initial rates. So these are the rates right after the reaction starts. Remember, most of the action, most of the change in concentration per unit time is occurring right at the beginning of the reaction. And so that's what we see right here. Now, this is in terms of the nitrogen. Okay. So the way we're going to solve the rate law is to solve the orders first. And remember, we're going to use the method of initial rates. That means we're going to take a ratio of rate laws for the different experiments. Okay. Now, when we set this up, you notice that we don't know what K is, but whatever it is, K over K, that just cancels. So we'll solve the rate constant later. Now, in this example, you notice there are two unknowns, N and M. Let's solve for N first. How do we do that? Well, we need a way to get rid of this unknown. The easiest way to do that is to find two experiments where the hydrogen concentrations are the same. You'll notice in experiment 1 and 2 that the hydrogen concentrations are equal to each other. The NO concentrations are different. So think about this before we get started. These numbers will be different, and so we'll get some number here, some ratio raised to the N. The hydrogen numbers will be the same. So some number raised to the M divided by the same number raised to the M, that's going to cancel. So let's go ahead and show that. So let's do this ratio of experiment 2 over experiment 1. I'm doing 2 over 1. You can pick any two experiments you want. I'm doing 2 over 1 simply because this number, the experiment 2 rate, is bigger than the experiment 1 rate. And so if I have a bigger number over a smaller number, that will give me just some number and not a fraction. But it's up to you how you want to work this out. You can pick any two experiments and set them up wherever you want. Okay, so let's just plug in these numbers. So here's the rate for experiment 2. I'm going to leave the units out because I don't want this to get too messy. The concentration for NO is 1.0 10 to the minus 2 mole per liter. And remember, this is raised to the N. The concentration of the hydrogen is 0.32, and that's raised to the M. Let's divide that by writing the rate law for experiment 1, which is the rate for experiment 1, 0.012 is equal to K. 5.0 10 to the minus 3 is the concentration of NO raised to the N, and the concentration of hydrogen, 0.32 raised to the M. Okay, So a couple things stand out. We're setting up a ratio here. It's all of this divided by all of this. And of course, you'll notice I don't know what K is, but it cancels. I don't know what M is, but whatever it is, 0.32 raised to the M divided by itself is equal to 1, so that just cancels. Okay, so what's left over? 0.048 divided by 0.012, that's a ratio of 4. And that's equal to 1.010 to the minus 2 divided by 5.010 to the minus 3. You work this out. This is 2.0 raised to the n. Let me pick this up a little bit. Okay, so what is n? N, let me show you this. So 2.0 raised to the 0 is equal to 1. 2.0 raised to the 1 is equal to 2. 2.0 raised to the 2 is equal to 4. And so, of course, that's what n is equal to. N is equal to 2. So what we can say is the reaction is second order with respect to NO. Okay, now that's just one power. Remember, we still need to go get that other power. So, as you can imagine, how do we find M? Well, let's go find two experiments. Go back up here. Let's find two experiments where the NOs cancel. So let's cancel the N and let's solve for M. So we want the hydrogens to be different. We want these numbers, NO, to be the same. So clearly experiment 3 and 2 will do that for me. Okay, so let's go ahead and set that up. Let's set up a ratio of experiment 3 over 2. Again, you can set it up however you want, 2 over 3 or 3 over 2. The rate for experiment 3, 0.096 is equal to K. For experiment 3, NO is 1.010 to the minus 2. Hydrogen is 0.64. And this is squared. Remember, we've already solved this power. For experiment 2, go back up, the rate is 0.048, and NO is 1.010 to the minus 2. The hydrogen is 0.32. So the same thing that we did in the first example. And of course, K's will cancel. And look at my NOs. Same thing. 1.010 to the minus 2 squared divided by 1.010 to the minus 2 squared. That cancels. And so you can see what's left over. What's left over is 0.096 over 0.048. This is a ratio of 2.0. 0.64 divided by 0.32, that's a ratio of 2.0 raised to the m. And so again, just by inspection, m, of course, has to equal 1. So we can say that the reaction is first order with respect to hydrogen. Okay, so let's go ahead and put all that together. The rate law is rate is equal to a rate constant times the concentration of NO raised to the 2 times the concentration of hydrogen raised to the 1. Now that's a first order with respect to hydrogen. I don't have to write the 1. I'll just go ahead and leave it like that. And so that's our rate law. Okay, let's solve for K. Let's solve for the rate constant. So if we divide both sides by the concentrations, these terms right here, we can solve for K. Again, the rate constant is a constant no matter which experiment you use. No matter what different concentrations you use, the rate constant is going to be constant. And so you can pick any experiment you want. I'll go ahead and use experiment 1. I'll use the data for experiment 1. And so the rate for experiment 1, 0.012. And the rate, I'm going to give myself some room here, mole per liter seconds. Now be careful, we're going to plug in the data for the NO. Now for experiment 1, the rate or the concentration for NO is 5.0 10 to the minus 3. Now remember, this is squared, and the concentration is also squared. So make sure you square those units. The hydrogen is raised to the 1. So for hydrogen, this is 0.32, and this is in mole per liter. Okay? So quick check of the units here, just to be on the safe side. It's really busy. So you've got mole over mole. You've got liter over liter. Don't forget, you still have these units here. So liter square goes on top. Mole square goes on the denominator. And don't forget, we still have those seconds in there. Okay, so when you plug in these numbers, don't forget to square this term here. So it's 0.012 divided by 5.0 10 to the minus 3 squared. And whatever that number is, don't forget to divide by this number for the hydrogen, 0.32. So the answer here, 1,500 liters squared per mole squared seconds. This is the rate constant. Okay, so one last scenario here. What if I do a fourth experiment? And what if the NO concentration is 1.2, 10 to the minus 2 mole per liter? And hydrogen is 1.4, 10 to the minus 2 mole per liter. what is the rate? And so now that we solve for the rate law, now that we solve for all of this and the rate constant, now we can do some other experiments. I mean, we can start with different concentrations and then we can calculate rates. So the rate will be 1500 liter squared per mole squared seconds times the concentration of NO raised to the 2 mole squared per liter squared times 1.4 10 to the minus 2 mole per liter. So I'm going to get up and get my calculator. And so the answer I get here, 3.0 10 to the minus 3. Check out the units. Mole squared over mole squared, liter squared over liter squared. And so look at the units that are left over. Mole per liter second. Okay, so let's do a quick recap here. So we solved the rate law. We solved the orders of the reaction using this ratio of different rate laws. We solved that it was second order with respect to NO, first order with respect to hydrogen, and I forgot, third order overall. And then we solve for the rate constant, and so now we've got the full rate law. And so the importance there is that now that we have the full rate law, now we can do other experiments, and then we can use the rate law to calculate, okay, what is the rate going to be?